So, hello everyone. So, we are going to start the part 2 that is the stoichiometry of product formation. So, let us quickly revisit what we discussed in the last lecture. So, in the last lecture we discussed that how to do stoichiometry balance using the concept of electron balance. So, we use the concept of degree of reduction and as all the electrons are conserved, it was used for the mass balance, or either you can say the electron balance. And this helps us to calculate that chemical oxygen demand. In addition, the what will be the maximum biomass and maximum product yield. Right. So, today we are going to proceed further this how to write particularly the product formation stoichiometry. So, before going further we will be seeing detailed stoichiometric representation considering a few steps which are energy source decimation, oxidative phosphorylation, biosynthesis, maintenance and dissipation. So, as you know, in the bioprocess there are several reaction steps, they correspond to the different metabolic functions through various metabolic pathways. And when we say this pathway means they are sort of reactions, and these reactions are either associated with ATP generation or ATP utilization. So, if it is exothermic, they will release the energy in terms of ATP. If they are endothermic, they will require the energy in terms of ATP. So, we will first quickly go through all these four: energy source dissimulation, oxidative phosphorylation, biosynthesis, maintenance and dissipation. So, first one is energy source dissimulation. So, what it says is you are having your carbon source, and carbon source is reacting with water molecule plus NAD, and it is producing carbon dioxide and NADH. And parallelly, as it is a oxidation reaction, it means the ATP is also generated. So, there are few coefficient here. The one is gamma S. What is gamma S? Degree of reduction of your substrate. So, if it is A here, so this much A NAD is required, and in addition you see one more term, that is the epsilon S. It says number of substrate level phosphorylation per carbon mole. So, depending what was the mole of carbon here, A, so this becomes ESA. So, this much ADP is converted to ATP during this oxidation process. For the water, why we are writing coefficient? Because there is no significant change in the stoichiometric coefficient of water molecule. That is why we are not quantifying it, rather we are generally writing coefficient. So, this NAD plus is converted to NADH plus H plus, and this substrate is converted to carbon dioxide during this oxidation process. Now, when we are discussing with energy source dissimulation, so whatever NADH plus H plus is there, that will take part in oxidative phosphorylation, and it says NADH plus H plus, they are going to combine with the oxygen, that will again form the NAD plus H2O. And in addition, there will be some more synthesis of ATP, that is equivalent to P by O, refers to the number of ADP phosphorylation per atom of oxygen consumed. So, what is the oxygen consumed here? 2B. This is 2B into P by O times ATP is also synthesized here, and theoretical value of, I have listed theoretical P by O value for acetate, malate and glucose. For acetate it is 2.25, malate 2.5 and glucose its value is 3. So, these are the first two steps. Energy source dissimulation, it says this your substrate is oxidized to carbon dioxide, and once NADH is formed, then next step it will convert to NAD in the oxidative phosphorylation process, and in the both these processes you say there is a synthesis of ATP molecules. Now, if I go to the next part, that is the biosynthesis. So, in case of biosynthesis, it requires this NADH molecule. So, in biosynthesis what is happening? You are having this carbon source, in addition you require nitrogen source, and NADH plus H plus is required to form this, let us say, biomass. Water is also synthesized, carbon dioxide is also there, and as this requires the energy. So, the energy is parallelly coming from the ATP is getting converted to ADP. So, it says during the biosynthesis it requires energy. So, energy comes from the ATP is reduced to this ADP and PI. Similarly, if I see for the maintenance, again it requires the energy is coming from the ATP to ADP, and the coefficient we are writing here as a C. Now, one more thing, there is a yield of ATP also can be calculated. It says YATP. YATP is defined as the mass of cell formed per mole of ATP consumed. So, it says delta X upon delta ATP. So, once this is in the mole, this is in the mass. So, we have to divide by molecular weight of biomass, that will be in the mole. So, this much mole of ATP will be converted to ADP. It says depending on the moles of biomass corresponding this YATP moles of ATP will be required to support this reaction, and parallelly this will be converted to ADP. So, these we discuss these 4 steps. First is energy source dissimulation, second is oxidative phosphorylation, third is biosynthesis, and fourth is maintenance and dissipation. So, for first 2 steps they produce the ATP, and last 2 they require the ATP molecule. So, as I told this, there is a yield coefficient for ATP also, and one value I have referred here is for the growth of E. coli, the YATP is 28.8. It says 28.8 gram of the cells are synthesized per gram mole of ATP consumed. Now, next, if I want to go for energy product metabolism, so we need to understand this. The cells releases a variety of chemicals into their environment, all originating from various metabolic pathways. And these products are result of energy yielding metabolisms, and depending on their synthesis during the bioprocess, they are referred as primary and secondary metabolites. If they are synthesized during the growth phase or along with the growth of biomass, we say they are primary metabolites, and when they are synthesized during the stationary phase, means independent of biomass growth, that is called secondary metabolites. One more thing, this catabolic metabolism in product. So, it says particularly this alcohol and organic acids, they are the result of catabolic mechanism. It means there will be the breakdown and these products will be the synthesized. In addition, few end products I have listed here, common end products, antibiotics, alkaloids, toxins and growth factors. Now, when we discuss about the fermentation or bioprocess, so typically we see this fermentation as anaerobic process, and in anaerobic process what is produced is the ethanol. How it is coming? First pyruvate is converted to acetaldehyde and the acetaldehyde is converted to ethanol. In addition, there is another route where pyruvate is converted to lactic acid or lactate. So, what it says, depending on the environmental condition, the same pyruvate can synthesize to ethanol under anaerobic condition, and when it is facultative anaerobic, it can synthesize the lactate molecule. So, here I have listed this few products like lactic acid, which are the producer, it is produced by the lactobacillus. There can be mixed acid as well, like lactic acid, acetic acid, succinic acid, formic acid and ethanol all together. There is a synthesis of butyric acid mostly produced by Clostridium, and in this addition there is a mix butanol and acetone. So, it says butanol, ethanol, acetone and isopropanols are synthesized together. In addition, there is synthesis of propionic acid produced by Propionibacterium. So, it says that you may have different class of fermentation like homolactic, mixed acid, butyric acid, propionic acid, so on and so forth. And so, for this there are different metabolic pathway and different producer organisms are involved there. Now, after understanding this how the products are formed, this now we will proceed to the product formation stoichiometry, and it says that it may be the primary energy metabolism. It means the main product is formed during this primary energy metabolism process. Second says this is indirectly formed from the energy metabolism, means directly it is not be part of the stoichiometry relation. Another option may be a product may be secondary metabolite, and third option is it is just a biochemical transformation. So, we will discuss first two class here. The first class is we have already discussed briefly in the last lecture. This is your carbon source, oxygen, nitrogen source, this is converted to biomass, water, carbon dioxide, and this is your product. So, this product is class 1 results of primary energy metabolism. So, the product is stoichiometrically related with your substrate here. So, this example we have already discussed. So, here how we calculate, let us say I want to calculate the yield of product Y P by S. So, this will be stoichiometric coefficient of product is F into, it says Ns is number of carbon atom in the substrate and Np is the number of carbon atom in the product. So, this comes Ns divided by A stoichiometric coefficient of your substrate into F divided by N P. So, in this way from the class 1 we should be able to calculate this yield factor, or if it is directly known the molecular formula and stoichiometric coefficient, then we should be able to directly calculate delta P upon delta S. Now, let us proceed to class 2. What is the class 2? The main product arises indirectly from the energy metabolism. So, it says here in the right hand side there will be no product. So, this in the stoichiometry relation with the substrate, there will be no direct product formation in the stoichiometry relation. So, it says this is your substrate, this much NAD plus is required, and how it is coming I will discuss in a while. This is leading to formation of biomass, carbon dioxide and NADH plus H plus. Now, how much NAD will be required? Which are being reduced? Gamma S. Gamma S is being reduced, and what is being formed? Product minus gamma P. What is the carbon fraction of substrate used for product formation is Z. So, this will be Z into gamma P. So, indirectly the term Z and gamma P is reflecting the product formation, but there is no molecular formula of product involved in this reaction. So, this is indirect Z into gamma P. So, the same NAD is required and NADH plus H plus is produced. D is the stoichiometric coefficient here. And as I know this process is there, it means ATP will also be synthesized parallelly. So, gamma P is the number of ATP generated by the product formation. So, gamma P into D, D is the stoichiometric coefficient here and same amount of ATP is formed. So, these are the two classes. In one case the product formation is related in terms of degree of reduction and carbon fraction, and in the first case through this stoichiometry relationship there is a biomass and there is a product in the same equation. Now, let us solve one problem to clarify this concept. So, it says this the chemical reaction equation for the conversion of ethanol to acetic acid. So, we are converting ethanol to acetic acid, this is the equation. So, this equation does not include biomass. Now, what it says? Now, I am going to produce the acetic acid using this acetobacter acetic, which has a composition of CH 1.8, O 0.5 and 0.2. So, what we have to write? We have to write the stoichiometry relation using your carbon source, that is C2H6O plus AO2. What is the nitrogen source? It says ammonia is the nitrogen source, BNH3 ammonia, and what is being formed here? There will be synthesis of first your biomass C times CH 1.8, O 0.5 and 0.2 plus there will be D CO2 plus E H2O. In addition, what it says that there is a product formation F, that is the C2H4O2. So, once I am able to write, this is the equation 1, this is the equation 2 in the bioprocess, right. Now, what it says, how does the growth of this culture affect the oxygen demand? So, here the stoichiometric coefficient of oxygen, let us consider 1, here the stoichiometric coefficient of oxygen is A. So, if you can calculate the value of A, then one should be able to comment how it is affecting the demand of oxygen for the acetic acid production. So, to calculate the stoichiometric coefficient, what is known to us is biomass yield 0.14, product yield 0.92. Biomass yield is 0.14, product yield is 0.92. So, let us write again this whole equation. This is C2H6O plus AO2 plus BNH3. This gives rise to C times biomass C H 1.8 O 0.5 N 0.2 plus D CO2 E H2O plus F time of your product, that is the C2 H4 O2. Now, what is given is Y x by S. What will be the Y x by S? Will be how much biomass is formed? C into molecular weight of biomass divided by molecular weight of your substrate, and if I calculate the molecular weight here, it will be 24.63 here, and molecular weight of your substrate is 46.1. Then this will be C into 24.63 divided by 46.1, and what is the value given is 0.14. So, straightforward we can get the value of C, which comes out to be 3.87. So, we got the stoichiometric coefficient of 1 C. Similarly, the yield is given here, yield of product is Y P by S is 0.92. So, this will be F into 2. So, how much product is formed here? F into molecular weight of product divided by the molecular weight of substrate. So, what is the molecular weight of product here? C2H4O2. This will be F into molecular weight of your product, that is 60 divided by 46.1 equals to the 92, and this gives rise to F equals to 0.71. Now, next step is we have to go for electron balance. When I am going for electron balance, so this will be W to gamma S minus 4A, degree of reduction is for nitrogen source is 0, equals C into gamma B, this is 0, this is 0, and plus F into 2 into gamma P, and if I calculate degree of reduction for gamma S, gamma B and gamma P, then for gamma S this will be 4 into 2 8 plus 6 14 minus 2 12 upon 2, this will be equals to the 6. So, gamma S is 6, gamma B will be 4 plus 1.8 minus 2 into 0.5 minus 3 into 0.2 divided by 1, and this will be 4.2, and gamma p will be equals to 8 plus 4 minus 4 divided by 2 equals to the 4. Now, if I apply here, so W is 2 into gamma S 6 minus 4 A equals C. C we have already found out 3.87 into gamma B is 4.2 plus AF is 0.71 into 2 into gamma P is 4. So, this gives rise to A equals to 1.31. It means without biomass, what was the stoichiometric coefficient for oxygen? 1, and with biomass the stoichiometric coefficient is 1.31. It means 31% increase in the oxygen demand. Oxygen demand. So, in this way, once we apply this electron balance, it becomes easy for us to solve this stoichiometric coefficients. So, here yield coefficient, electron balance, they are very helpful. In addition, if required, we can go for carbon and nitrogen balance, but typically we avoid this hydrogen balance. So, I will stop here. So, today we discuss this stoichiometry of the product formation. So, before we discuss different classes of the product, class 1 the product is the part of stoichiometry relation, class 2 the product is indirectly part of stoichiometry relation in terms of degree of reduction gamma p, and then we practice one example the how to apply the concept of yield coefficient and electron balance to find the value of stoichiometric coefficient. So, here we calculated the stoichiometric coefficient C, stoichiometric coefficient F, stoichiometric coefficient A. So, I will stop here. Thank you so much.